So, welcome everyone to the second part of the lecture on Lecture 9 in the Internet Seminar, which is about the Hardy Littlewood maximal operator. So, you got to know the Hardy Littlewood maximal operator in the last lecture. It's our principal player for this week in order to derive further results. And so, we checked that the Hardy Littlewood maximal operator controls averages, and we used it in LP bounds. So more specifically, we proved that this Hardy Littlewood operator was bounded on LP if P is larger than 1, and there was a weak type estimate on L1. And then we used the weak type estimate to derive Lebesgue differentiation theorem, which says that if I have a locally integrable function, then these what I call rough averages, so simply averaging a function over the ball around x of radius t reproduces the function u itself when t goes to 0 at almost every x, and these points where this works, I call them Lebesgue points. Okay, in the proof, you've seen that the proof uses two facts. It uses the fact that you can approximate locally integrable functions by good functions, continuous functions in this case, in which the reproducing via averaging and sending the scale to 0 is elementary. But then in order to do at the same time the limit in the scale and the limit in the functions that approximate the given u in the L1 topology, there is a two-parameter limit hanging around, and there is some uniformity with respect to the two parameters needed in order to master the proof of this theorem. And mastering this two-parameter limit is precisely what the Hardy Littlewood maximal operator did for us, because roughly speaking it eliminates one parameter from the game because it takes the soup over all scales and still you get something good. Okay, so that was somehow the game to be played, and I hope that this also shows why in proving this result you need something like an estimate on the maximal operator. And so I'm going to start this lecture by deriving two consequences of Lebesgue differentiation before we move on to other things and going to use more about the maximal operator. Okay, so 911 is the following corollary. It's about smooth averages. Okay, so I told you there are rough averages, are convolutions with respect to the normalized characteristic function of the unit ball, and then there's smooth average where you replace this characteristic function by a smooth function. Okay, so more specifically, suppose that theta is a CC infinity function. It's normalized to integral 1. And I'm going to have u on Rn a locally integrable function. And then I can say that, well, the smooth average at scale t was just this convolution evaluated in x. This is going to tend, as the scale goes to 0, it's going to give me back u of x. And this works again for almost every x in Rn. You could even be more precise, as the proof will show. This works at all Lebesgue points of u. Okay? And I'm going to do the proof just to show you once again that the Hardy Littlewood operator is really the one that rules all sorts of averages that we're thinking of. And so we're going to play the corollary for smooth averages. We're going to play it back to Lebesgue differentiation. Okay, so let's suppose that I just pick a ball of some large radius around the origin that's going to contain the support of my function, and then I just start estimating, a little bit similar to why this in fact was a stronger statement than proving convergence of the averages almost everywhere. Okay, so I'm gonna take a look at that, and this is absolute values I'm gonna take in a second, but first let me use the crucial observation that this normalization of theta really is what is used to call these object averages. Okay, so with theta, by the transformation rule, also the theta t have integral 1 for every t. And I'm going to use that in order to write the differences of these two things as theta t of x minus y applied to u of y. This was just writing out the convolution, but then I can subtract off u of x inside the integral. And this is where I'm using that this is an averaging operator because the integral is 1. And then it's almost there. I'm going to take absolute values. I'm going to throw absolute values inside. I'm going to remind myself that this function, theta t, is in a way that if theta t of x minus y is non-zero, then actually I'm integrating on a ball centered in x. This is by the translation. And then by the dilation, the radius of that ball is going to be r times t. And then I'm going to pull out the theta in L infinity norm. This is going to give me theta in L infinity norm, and this gives me 1 over t to the n from the way that these modifiers were defined. And then I sneak in another r to the n in order to make this an average. So in the next line, I'm estimating by theta in L infinity norm. I'm going to multiply it and divide by r to the n and by the measure of the unit ball. And if I divide that out, then together with a t to the n is going to produce exactly the measure of this ball. So I can estimate this by the average on the ball of radius rt, and I'm going to do u of y minus u of x dy. And now you see this is just a constant depending on the theta, and that thing here is going to tend to 0 as t goes to 0 by Lebesgue differentiation. Okay, so as t goes to 0, this goes to 0 by 9.9. Probably you should turn on the lights now because it got really dark, right? So a second corollary that I find interesting is about one-sided averages. Okay, so that's a thing I'm only doing on the real line. So suppose that u now on the real line is locally integrable as always, and then the following thing is going to happen at almost every point. So then if I take the integral from x to x plus h over u of y dy, and I'm going to normalize by dividing over h, and now h can be positive or negative and the integral becomes oriented as usual. Then taking the limit as h goes to 0, this gives me back u of x, again for almost every x in R. You see, so that's somehow one side of a fundamental theorem of calculus. And once again, the proof is super easy. I have some room. I try to squeeze it in one line because it's the same strategy over and over again. The only thing that ever is going to happen in the proof is that I'm integrating with respect to a measure that is normalized if you put the 1 over h in the measure. So I'm just taking the difference of the integral with what is supposedly the limit. I take absolute values. Then I play the same trick once again. I'm going to take that u of x and move it in the dy integral because averaging preserves constants. And once it's inside, I'm going to use the triangle inequality. I'm going to make that integral an integral over a ball of radius absolute value of h. So if h is positive, this would be going from x minus h to x plus h. Inside of the integral, I have u of y minus u of x dy is just moving absolute values inside. In front of the integral, I had 1 over h with absolute value, which is half of the measure of this set. So make it an average and multiply by 2, then all is fine again. And then you see you're back in the situation of Lebesgue differentiation. So as h goes to 0, again by Lebesgue differentiation, that thing goes to 0. And so you have the proof. In case you were still lost in this proof because I didn't finish it, put the square here. Okay, so it's just as easy as that. And now, why am I saying all these things with the one-sided averages to you? Is because which functions are of this type that are somehow oriented integrals of locally integrable stuff? That's something that we saw when we studied continuity of Sobolev functions on a real line. Or in particular, the following is going to apply for h1 functions on a bounded interval. But we can be a little bit more general. Okay, so as a flashback to, I think it was Theorem 314. And what you saw there is if I have u, a L1 function on a bounded interval, okay, so AB is going to be bounded interval, and this L1 function on the bounded interval is weakly differentiable, so u prime is a weak derivative, and the weak derivative is L1 again, then this function has a continuous representative with which I'm going to identify it. Okay, and this representative is given by, well, it's the antiderivative of the weak derivative. So it's the integral from, say u of a plus integral from a to x over u prime y dy. This is how we could write it, and this u of a was only defined for the continuous thing because this guy had an extension to a continuous function on the closed interval from a to b. Okay, so this is how we can write u. And now this u, this function on the right-hand side, fits exactly in the previous result. And you see, in order to get the integral from x to x plus h and divide it by 1 over h, I have to do an ordinary difference quotient of u. Okay, so I can put these things together, and what I can prove is 9.13 is also corollary about absolutely continuous functions. Okay, and so in the setting above, I can look at u of x plus h minus u of x for this Sobolev function, and I divide it by h, and then as h goes to 0, this is going to give me back u prime of x for almost every x in AB. Okay, so this result has to be read in the right way. It says that if I start, in particular with the h1 function on AB, but it could be more general as written here, then this function has a continuous representative. This continuous representative is differentiable in the classical sense at almost every point, and the derivative in the classical sense just gives me back the weak derivative defined via test functions. Okay, so it's a beautiful result, and it's sort of the second part. I mean, 314 we called fundamental theorem of calculus for h1 functions in particular. It was one part. It was the part that I can get the function as antiderivative of its weak derivative. Now you can also go the other way around. You can differentiate function in the classical sense, and you get back the weak derivative. Okay, this is almost direct from this result here. The only difference being that here I'm working on a bounded interval, whereas here I was working on R. But then, because once again this is somehow a local claim, you would just apply the result here to the extension by 0 of the function that is written here. So take this function, extend it by 0, and then use the other result. All right. That was short and sweet about differentiation. Do you have questions? Okay, some people outside being really loud. Yes, they're getting excited about what is going to happen next in the internet seminar. Let's see, what is going to happen next? I want to get back to something that you've seen in lecture 4. And, remember that somehow the whole story I'm trying to tell in this lecture 9 and then also in lecture 10 and 11 is that we're trying to incorporate a different type of mathematics into the theory that somehow hovers around elliptic operators in divergence form to prove in the end the Kato theorem for square roots. And what I'm going to do in this section is that we're going to get back to quadratic estimates, and we use the maximal function theorem to get some further insight or somehow take a different perspective on quadratic estimates and then see what we can do. And so 9.3 is about quadratic estimates and Carlson's lemma. All right. And so I look back to, well, it's another flashback. Flashback 2. I'm getting back to, now I have to remember the number, Theorem 416. Theorem 416, say with theta a CC infinity function. In 416, theta was a Schwarz function. Don't have to look it up. I'm going to tell you what it was. 416 was about quadratic estimates with respect to convolutions. Okay? And I'm going to write this 416 results in a slightly different way, and then this is going to be equation 9.8. It says that if I integrate over the upper half space, and so for me, upper half space here, this guy, this is going to be Rn cross 0 infinity, and the variables that are living in this upper half space, it's going to be an x and it's going to be t. And then I can write out theta of t convolution with u at x squared dx dt over t. Back in lecture 4, we didn't write out the inner L2 norm squared with respect to x. We just wrote integral from 0 to infinity with respect to dt over t of theta t convolution u L2 norm squared. I just wrote it out because this is going to be helpful for the new perspective on this result I'm going to take. And it said in particular that you can bound this by u in the L2 norm squared, and now u was in L2 of Rn. So that's a result that we proved using Fourier analysis. There also was a square root of t in lecture 4 because it would fit better with the functional calculus of Laplacian. Well, you do change of variables up to constant because of Haar measure. It's going to be the same. Okay, so safe to say that in Theorem 4.16 we proved this sort of estimate. And so when you compare it with what you see on the upper board, right, the question that jumps to your mind is there a relation to smooth averages? And so is there one? Red color is going to come. this is not a statement about smooth averages. Okay? A priori, this wasn't a statement about smooth averages, because what did we assume in Theorem 416? Okay, so 416 assumed a cancellation property of theta, namely that the integral on Rn of theta would be 0, which is the complete opposite of any sort of averaging property, which you saw nicely in this proof over there. These are averaging results because the integral of theta is 1. You could normalize it if the integral of theta would be anything else than 0, but the cancellation property is the complete opposite of the averaging property. Okay? So this is the opposite of the averaging property. Okay, so opposite of averaging property, which would be that the integral of theta would be 1. Okay, so this is a statement, but it uses cancellation hidden in the properties of theta. And it's not going to talk about averages. And in fact, the result 9.8 is never going to be true if you're talking about averages, because suppose that theta would be related to averaging, then you know that the modifications of u converge to u in L2. Okay, so given u, if t is small enough and u is not 0, then I'm going to have that theta of t convolution with u in L2 norm squared is going to be larger than 1 over 2 times u in L2 norm squared, just because this guy converges to this guy in L2 norm. Okay, so here L2 norms are not written out, but then you see if you integrate this with respect to dt over t, which would be missing in order to produce this term, then here you're integrating a constant with respect to dt over t. And so unless u is the 0 function, this is going to give you infinity. Because it's just a constant integrated with respect to dt over t. And so there's no way that you're going to have 9.8 for averaging operators. Agree? That's all I wanted to say for today. Stop. Now I want to do something else. I want to save 9.8. And my main question is going to be the following. See, it was a property of this measure that this failed. So my question is, can we replace the measure dx dt over t by some other Borel measure d nu of xt on the upper half space, such that the corresponding estimate does hold true for averaging operators. Okay, such that 9.8 does hold for averaging operators. Right? That's my question. So I want to save this estimate at the expense of replacing this by some other measure. And that's a good question. It's going to be easier, and it's also going to be more useful for the things we want to do in later lectures, to look at this problem not in a continuous setting where the scale t can be any positive number, but we want to look at it in a dyadic setting where the scales are dyadic numbers. Okay, so from now on, I'm going to look at this question in a dyadic setting, So scales for averaging will be numbers 2 to the j, where j is an integer. All right, so in order to tackle this problem in dyadic setting, we need to introduce some dyadic objects to work with. Okay, so everything that we've seen before for the Hardy Littlewood operator is now going to become dyadic. So there's only going to be dyadic cubes instead of balls, and there's only going to be dyadic scales instead of arbitrary scales positive. Okay, so we need the corresponding notation. This is a cube, right? In fact, it's a collection of cubes. This is going to be the collection of all families cube sub-index 2 to the j, and this j guy is going to be called generation. Okay, and these elements in cube j, they are dyadic cubes of side length 2 to the j. So this is the collection of dyadic cubes, and cube j is going to be the collection of all cubes that look like this. You take a center, or you take a corner x in integers to the n, you multiply it to the scale. This gives you a mesh of points that have distance 2 to the j in all coordinate directions, and then we're going to make these guys half open so that they're going to form a partition of r to the n. Okay, so these are the cubes, and if Q is such a dyadic cube of generation 2 to the j, then L of Q is always going to be the side length. Then the side length of this guy is 2 to the j. Okay, so these are the cubes I'm using. It will be convenient for mostly notational purposes to also introduce dyadic cubes of generation t if t is not a dyadic number. So if t is positive, then I set cube collection of generation t to be cube collection of generation 2 to the j, where j is the unique integer such that t is larger than 2 to the j minus 1 and goes up to 2 to the j. Okay. For every t there's a unique integer j with this property, and then it works. That's our definition. Okay, and of course for any t positive we have that r to the n is the union of all cubes of generation t, and this is a partition. So it's a union of pairwise disjoint elements. Okay, so these dyadic cubes, they're going to play the role of balls in our dyadic setting. And by the way, I should say, in case you ask, why did I start with maximal operators in continuous setting and now I'm going back to a dyadic setting? I could have started with everything dyadic in the first place. Well, the reason is that many problems in analysis, they have like a continuous and a dyadic version. And sometimes the dyadic version is easier to study than the continuous version. Sometimes it's the opposite. One thing that is good in the dyadic world is that the equivalence of balls, these are always unions of sets that are pairwise disjoints, and there's a hierarchy. Okay, so for every generation fixed, you can write Rn as a partition of the cubes of generation t. If I have any point and I pick any generation, then I'm going to find the dyadic cube of that generation that contains my point. And then there are subcubes, and there are supercubes, and they are ordered. Dyadic cubes have the property that either of different generation, either one is contained in the other, or they're disjoint. So you have this hierarchy. We're going to see it on pictures later on. And so I think it's important to see how these maximal operators and averaging operators, they look like if you decide to go full dyadic. Okay, and so now for U, say U is a L1 log function on Rn, and x is some point in Rn. Now I'm going to introduce averaging operators in the dyadic setting, and I'm going to introduce a maximal operator in the dyadic setting. Okay, so the averaging operator, dyadic averaging operator at scale t. This goes as follows. Well, I call this A t of U at x. This is going to be the average of U on some cube. The only thing I have to tell you is which cube am I going to take. Okay, and because I work at scale t, this Q is the unique cube of generation t that contains x. That's it. There's only one. So you take the only guy that is reasonable. And then you define the dyadic maximal function or the maximal function. You're going to define it as A of U at x. Well, it's the soup over all generation, and you take averages at scale t of the absolute value. It's just mimicking what we did for the Hardy Littlewood operator. Then this guy is going to be called dyadic maximal function of U, and the operator that associates with U, the dyadic maximal function, this one I can call dyadic maximal operator. All right, so this is how the dyadic guys look like. Okay, we try to get a little bit comfy with these dyadic things, then we make a break, and then we prove a nice theorem, and we're going to answer in the best possible way the question which sort of measures make my initial question work. Yeah, okay, so I'm going to explain something and you don't get lost. So while I'm cleaning the board, you could think about two things, like is the dyadic maximal operator going to be bounded on LP spaces, and is there a version of Lebesgue differentiation if I use dyadic averages? In other words, can I retrieve the function U from looking at dyadic averages with a scale going to 0? What's your impression on that? Is it going to be hard? Or is there a nice principle? Well, if you think of cubes, cubes are contained in balls of comparable size. Okay, so averaging over cubes or averaging over balls shouldn't be an issue, and then it shouldn't also be an issue if the cube is centered at x, or if x is somewhere inside the cube, or if x is a corner of the cube. Shouldn't really matter. And this is all these sorts of comparability is what is indeed true. Okay, and this is a simple proposition saying two things. First of all, you control the dyadic maximal operator or dyadic maximal function up to a constant you control by Hardy Littlewood maximal function, and some constant that makes it work is maybe omega n to the n over 2, but doesn't really matter, just dimensional constant. And then the other thing is dyadic averages of u at scale x as t goes to 0. They're going to give you back u of x, and this is for almost every x in Rn. Okay, and of course u is a locally integrable function, as it is all the time. Right, and so the proof is not complicated, because look at the first statement. This is a soup over all scales, so let's work at a fixed scale first. ATU of x, this is the integral average on some cube, and so measure of the cube is 1 over side length of the cube to the power of n, and then you take u. Okay, and so let's put absolute value here and put absolute value here. All right, and so what is this cube? Well, Q is unique dyadic cube of scale t that contains x. So Q is going to be a subset of open ball centered at x with diameter of Q to be the radius. You just pack the cube into a massive ball with the largest possible radius that you need. And then this guy here, the diameter, this is like square root of n times the length of Q. Okay, so if in the next step I want to bound that by an integral average on this huge ball, of u, well, measure of the length of cube to the n I already have. I'm just missing the constants that come in the measure of this ball, so I'm just missing omega n, and then I'm missing square root of n to the n. And then you see this is an integral average on a ball, so it's controlled by the same number times the Hardy Littlewood operator. And that's it. Yes, please. Yeah, maybe you should put a 2 in there, and then it's going to be 2. You're right, because the ball is half open. Maybe you should do a little bit. Well, there's no points in the ball that have distance larger or equal to square root of n times the length. So I think it's correct with the length. You go in any direction, you're not close. So the only way of achieving this distance would be if you're one corner of the cube and you are on the other side sitting in the corner. And this is never going to happen. We're going to fix it in the break. I'm not going to stop the lecture for this. We're going to fix it in the break. Okay, well, it doesn't matter what constant is sitting here. Let me just finish the proof of this, and then we make the break, and then we can talk about it. And I'm going to tell the answer to everyone after the break. The second part is just as easy, because if you take AT of u at x and you subtract off q of x, then you write it as usual as an average over q. Q is the unique cube that gives rise to the definition of this object. Then it's going to be u of y minus u of x dy, and then you play in absolute values. You're going to make it less or equal. You're going to make absolute value here, and then you change this guy to the ball of the first part of the proof at the expense of putting the respective constant there, and you see you control this difference by something that works for Lebesgue differentiation. So as L of Q, and L of Q is comparable to T, so as T goes to 0, L of Q goes to 0, and as L of Q goes to 0, Lebesgue differentiation says that this goes to 0 for almost every x. Okay. Now this works for almost every x in Rn. All right, so we have this proof. We know, now we could prove further results because the pointwise control of the dyadic maximal function by the Hardy Littlewood one allows you to prove LP bounds for this guy just by domination. And we're going to use that after the break. So let's do a 10 minutes break, and then I'm going to tell you more about averages and measures. Then let's go on. You ready? I'm ready. Okay, so we have the dyadic maximal operator and function in place, and now we should get back to our question about measures on the upper half space that make the quadratic estimate with respect to this measure work for averaging operators. And the averaging operators in this case will not be the theta t convolution with U, but will be the dyadic averaging operators at scale t. Okay, and in order to get a feel for anything that's going on here, let's make the following drawing. Okay, so this is Rn and this is the upper half space. Now assume that there's some cube. Okay, so imagine we're seeing a cube down here. Now imagine this Q is a dyadic cube. Now if a point sits in here, then depending on the scale I can use this cube, or I can use subcubes that are smaller or smaller and smaller for smaller scales. And now these subcubes, they're all sitting inside of Q and I don't see them on the board. So there is an efficient way of sort of visualizing what is going on here. And it's a picture in which you see that you can cover the upper half space by boxes, and in this box all dyadic children of this Q are also going to be appearing. Okay, so imagine that this cube has like unit length, and then this is a 1 sitting over there. And now if the t is between a half and 1, then I would use this cube as the defining cube for the dyadic averaging operator at scale t. And I'm going to visualize that here by drawing a box of this type. And if t and x are in here, then this is the cube I'm using. Now if I jump to the next scale, okay, so scale is always this one is contained and this one is open. Now if I jump to the next scale and I'm taking a point in here, then I'm not going to use this cube anymore because it's too big. I have to use one of the subcubes of Q of one generation down. And so I can visualize that by like that. And so if x and t is sitting in here, then I use this cube sitting somewhere here for the averaging operator. If I'm sitting here, I use this cube. And likewise, if I break the scale down once again, 1 over 8, then there's 4 possible cubes I'm using, and they look like this. And then for even smaller scale, things become smaller and smaller and smaller. Okay, and so these boxes that are sitting here, they give a partition of r to the n plus 1 plus this is the union over all q in over all j in Z, and then I'm taking the union over all these boxes q dyadic cube of generation 2 to the j, and I'm taking the box q cross length of q over 2 length of cube. Okay, these are my boxes, and this length of q here, this is just, I could equally write it down because the length of Q is 2 to the j. This is 2 to the j minus 1, and this is 2 to the j. Okay, and these boxes here, these guys, I'm going to call Whitney boxes. Okay, and then it goes on, the picture goes on in all directions, and the picture is somehow scale invariant, so it doesn't really matter what the scale of u are, is this unit scale or something else. Picture just looks like this. And the thing is that if x and t is contained in a Whitney box, then this means that the dyadic averaging operator of scale t at x is going to use exactly the box Q. Okay? So that means that no matter which function I take, dyadic averaging as a function of t and x is going to be constant on these regions. So it's a constant functions on these rectangulars. It's a Borel measurable function. Okay, Borel measurable is not what I really want to say. It's just a side remark so that I'm not doing anything stupid here. And now suppose that this estimate on quadratic estimates would be true. Suppose now V would be a Borel measure such that there exists a constant C, positive, with the following property. The dyadic version of my quadratic estimates from the beginning, it would now be ATU at x squared integrated against this measure nu, and I want that to be smaller than u in L2 norm squared for every u in L2 Rn. Right, that's the hypothetical estimate with a new measure I should be looking at now in the dyadic setting. And now, just hypothetically, suppose that the measure would have this property. Now I can test with u being the indicator function of a dyadic cube, Q, where Q is any dyadic cube, say, of generation 2 to the j. Okay, so suppose in my picture that removing all these scales, just writing L of Q here, that the cube is this one. And I'm going to test this estimate with this L2 function. So what am I gonna find out? Well, ATU of x is going to be 1 on a substantial part. For example, ATU of x is going to be 1 everywhere here, because in this case I would use Q itself to define ATU of u at x. But ATU would also be 1 here and here, because the cubes I'm using to define ATU of x are subcubes of Q. And so I average the constant 1 function on a subcube gives me 1. And in the same way, it would also be 1 here, 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 and here. And actually it would go 1 everywhere on this region. So this would be equal to 1 on Q times the box reaching all the way down. Okay, and these boxes people call Carlson boxes. Well, if AT of u for this specific u is 1 on the Carlson box, then I can look back to 9.9 and I see that on the left hand side I'm getting something that's even bigger than the possibly, well actually it is not, but anyway, it's just a one function on this guy, so this integral dominates the measure of the Carlson box. And on the right hand side, I'm getting a constant times the L2 norm of this indicator function squared, which is just the Lebesgue measure of the cube. So I get this estimate with a universal constant for every dyadic cube. And so that's a condition that a measure can satisfy, but doesn't have to satisfy it. But this is necessary for 9.9 to hold. And so we have a necessary condition, namely, if 9.9 holds, then V, the nu, has to be one of the measures that Leonard Carlson introduced back in the 60s in order to eventually arrive at his world-famous solution of the corona problem in complex analysis, and hence these measures are called Carlson measures. Okay, and so that's definition 9.17. Nu, always Borel measure on the upper half space, is a Carlson measure. I could also say a dyadic Carlson measure if the soup over all dyadic cubes of the quotient of the measure of the Carlson box and the Lebesgue measure of the cube, if this soup is finite. And if this soup is finite, one calls it the Carlson norm, index C for Carlson, of the measure. Fine. Only measures that can satisfy that 9.9 are Carlson measures. dx dt over t is not a Carlson measure. So Carlson measures have this property that somehow the measure of these very specific boxes where the x variable in size is linked to the t variable, these measures somehow, these boxes somehow in measure behave like something just living down there with respect to the Lebesgue measure. This is what this Supremo thing says. Okay, so in order to get a feel for the notation, there's an example that I'm going to send to the exercises. I think you can just appreciate it if you do it yourself to get a feel of what these Carlson measures do and how they somehow have this property that most of the things that are happening here somehow concentrates on the boundary in this measure theoretic sense. So a non-trivial example of a Carlson measure would be as follows. You take d nu of xt to be the characteristic function of a certain set gamma, and then you integrate dx dt over t. So it's a modification of the dx dt over t example by a density, and the density is an indicator function of the set gamma, which is a cone. So it's a cone with a tip at the origin in Rn. So it's more precisely it's this set here. It's a huge challenge making the diagonal correct. But so this gamma is the set, this conical set. Okay, so this is all xt with the properties that x in absolute value is less than t. Okay, so that's one example of a Carlson measure. We're going to see other Carlson measures later on in the lectures. And so with this being set up, what I want to do in the remainder of the lecture is to prove a beautiful theorem. Well, as I always say when I do this proof on the board, for me it's a big theorem, but for Carlson it was just a lemma. So it's the dyadic Carlson lemma. And it says that not only is this condition necessary is also sufficient. So it characterizes the measures for which this works with averaging operators are precisely the Carlson measures. Okay, so more precisely, if nu is Carlson, right? As always, that's how the cool people say it. You don't say it's a Carlson measure, you say it's Carlson. Okay. So if mu is Carlson, then you have this estimate 9.9, and the constant c is a dimensional garbage times the Carlson norm of the measure. Okay, so then the integral over Rn plus 1 plus of a of tu x squared with respect to this new measure is controlled by a dimensional constant Cn times the Carlson norm of the measure times u in L2 squared, and this works for all u in L2 of Rn. Yep. Do you have questions on that? Shall we do the proof? You want to see it? It's a nice proof. So I learned this proof. I learned this proof from Andrew, by the way. Andrew gave the lecture last week, and okay, it's a shame he cannot give this lecture as well, because I learned from one of his papers back as a student, I learned this dyadic proof. So the proof is a real analysis proof, so, you know, okay, how much time do I have? Half an hour? That's okay. Time for one anecdote at least. If you've seen other lectures of me, you probably know the story. I'm sorry for that if I'm repeating myself, but I find it just too accurate to describe what I'm doing. So I realized that my wife was explaining to someone else at her work what I was doing, and she said, you know, my husband solves problems by dividing a problem on a region into a problem on cubes, and then he makes the cube smaller. In every step he doesn't do anything but making the cube smaller, and in the end he doesn't do anything but the problem is solved. This is how his work works. And in a way, sometimes you get the feeling when you see these arguments on cubes that it's not completely off reality. Okay, and somehow in this spirit, but we have to do something, we have to be clever at some point. But we're going to prove that by splitting, first of all, everything into dyadics. Okay, so I'm going to look at the family of dyadic cubes of generation 2 to the j, and I'm just finding an enumeration of these cubes. So I'm going to write them as qjk, and k is some running index. It's just the enumeration to put these guys in a list. And then I start on the left-hand side. Integral on Rn plus 1 plus a of tu x squared d nu xt. I write it into dyadics because this function is just constant on all these regions, right? So in the first step I split the integral in the t direction into the dyadic numbers 2 to the j and so on and so forth. And so j goes from minus infinity to plus infinity. And then, so this is somehow splitting the t integral into these layers, and then on all of these layers I split integration into integration on the Carlson boxes. And the Carlson boxes, they are fixed in height, so they only depend on the cube on Rn that determines, these are the Whitney boxes. Whole thing is the Carlson box, but this is the Whitney box. Okay, so if I'm splitting this into Whitney boxes, then I get a sum in k, and then I'm getting stuff. I'm getting the value of the dyadic averaging operator, but if I happen to live on a Whitney on a region of the type 2 to the j minus 1 to 2 to the j times one of these cubes, then the averages is just qjk, and I'm getting u dy. So these are the values that the averaging operators take on these slices when k is running, and the region on which you use exactly this value, well, this is if qjk, if this is qjk, then you're going to use it over here on this thing, okay? And so this is then going to be 2 to the j minus 1 to 2 to the j. Okay, so it's this region. So function is constant, so if I do the integration, this is going to be just a measure of qjk cross 2 to the j minus 1 to 2 to the j, end of the story. Okay, so this is how the integral splits into all its elementary things. And then for a long time in this proof, we're mostly working with numbers. So I'm going to call that sum from minus infinity to sum to plus infinity, sum in k. And then I'm going to call these numbers ujk, maybe with an absolute value, I'm not sure, but I should be consistent with what I'm trying to do. Yeah, so I shall call them ujk squared, and these numbers I'm going to call new jk. So in other words, if I use two colors, then ujk is just this integral average on the cube qjk, and new jk is the measure of this Whitney box. Okay, so that's how the symbols go. And now, what do you have to do? Sometimes in these proofs, the most important thing is to know your enemy. Okay, so this is hard, and I'm going to continue with hard in a second, but once I have to know, first I have to know my enemy. And my enemy in this case starts with an O, it's overlap. My enemy in this proof is overlap. And why is this? Well, if you look at that, you could just say I use the Carlson condition on the measure of these Whitney boxes, because these Whitney boxes, well, they are smaller than the Carlson box where you go from 0 to 2 to the j, and then I could replace up to constant the new measure of the Whitney box by just a Lebesgue measure of the cube. But if I would do that, then for fixed k I would still be fine, because these cubes would be a partition of r to the n, but it would always partition all of r to the n, and I'm still summing in j. So I create huge overlap. I'm not working in the picture over there, but I work just at the boundary, and I not just have the one flat cube, but I also have all of these subcubes. So I'm summing a tremendous amount of time the same thing. And so therefore overlap is my enemy in this proof. I have to make sure that I'm not creating overlap before I use the Carlson condition. And so in order to not create overlap, I have to somehow arrange the cubes qjk in a different manner. And I'm going to arrange them according to the size of ujk. Okay, more precisely, it may or it may not happen that given a threshold lambda positive, it may or it may not be that the average number ujk in absolute value is larger than lambda. It can be true, depends on lambda and it depends on the cube. But yeah, this can be true or it can fail. And I want to say something about the case where this is true. Because if this is true, then the average of u on qjk is already larger than lambda in absolute value. So the dyadic maximal function is also larger than lambda. And actually it's larger than lambda on the entire cube qjk. Because on the entire cube qjk, for every x in this thing, qjk appears as one of the cubes that I'm using. So I claim this implies that the entire cube qjk is contained in the set, well, actually a super level set of the dyadic maximal function. Right? If already this guy at one cube is larger than lambda, then the maximal function is going to be larger than lambda as well on every single x, where at one point, for one scale, I'm choosing this cube, and so this happens at every point in the cube. Okay, so now there is this pointwise control of the dyadic guy by the Hardy Littlewood maximal guy. So if the dyadic guy is already large, then up to constant, Hardy Littlewood has to be large as well. So this is a subset of all x in Rn for which Hardy Littlewood of u at x is larger than lambda over c, and c is this constant that appears in statement 914. So omega n to the times n to the n over 2. It doesn't really matter. Now this tells me something very important. Because how large is this set? It can be incredibly large. But what do we know about its measure? Well, you know, u is a L2 function. Hardy Littlewood of u is also L2. So Markov's inequality says that this set cannot have infinite measure. It can only have finite measure. Okay? But because this set has, you agree that it has finite measure? Now, if this is finite measure and it contains these cubes, this means that these cubes cannot become arbitrarily large. So it means that there is an upper bound on the generation 2 to the j of such cubes. Okay, where the word such is making reference to the property that the average was large. Right? These cubes can become large, but they cannot become arbitrarily large, and you can say how large they become by taking like nth root of the measure of this set. So that means that whenever I have such a cube, okay, so such a cube is once again a dyadic cube with this property, then either this is already in a sense the largest cube with this property, it can have a dyadic parent, so a larger dyadic cube that contains it, that still has the property, and even the parents can have parents and parents and parents that all have this property, but at some point it has to stop because of the finite measure. So each cube with a property that this average is larger than lambda is contained in a dyadic cube of maximal size that has this property. Okay, so these cubes I'm going to call maximal. So each such cube is contained in a maximal one with this property. Alright, and so now my idea is I'm going to eliminate this overlap by looking at a specific cube. Then I go up in the hierarchy until I find the largest guy that has this property. And then I'm just looking at the largest guy of all such family trees. Okay, so first of all I can say every cube with this property is contained in the largest such cube. And then for fixed lambda, I can say that Q lambda m, this is an enumeration of these maximal cubes. Okay. So Q lambda m is the collection of all maximal dyadic cubes with a property that the average of U on that cube is larger than lambda. Now the good thing about maximal cubes is they're pairwise disjoint. There's no overlap on maximal cubes because for all sorts of dyadic cubes it is either true that they're disjoint or one contains the other, but by maximality the second case can never appear. If one of these guys would be contained in another one, it wouldn't be maximal anymore. So these are pairwise disjoint. And that's the fantastic thing here. Okay. Okay, and that has nothing to do with this specific setup. It's just in this process of working on the maximal cubes with respect to property. If you work in dyadic world, then maximal cubes exist under very mild conditions. You just need something like that that says that the family has to stop at some point up there in my picture over there, and then you get these maximal cubes and they're pairwise disjoint. Alright, so with this at hand, I'm going to get back to the estimate, and I'm not going to use the Carlson condition, but I try to be more clever, and I try to not use any overlap until the right moment when there's no overlap anymore. Now, one thing should look kind of strange for you, namely the fact that I use this lambda, but there's just, where's the lambda over there? It's just not there. So now I'm using the same trick as in the layer cake formula. I just artificially write these numbers, ujk squared times nu jk. I just write artificially as an integral. I write it as the integral from 0 to ujk absolute value. I take the derivative of the square function and I leave the constant where it is and I say d lambda. So this way, through this integral, I introduce the parameter lambda, and now I'm going to use monotone convergence in order to see that this way of introducing the lambda perfectly fits with the idea that I should order the cubes according to the size of the average. And if you want to pull the sum in by monotone convergence because all is positive, only thing you have to do is you have to write this integral as an indicator function. And so what you're getting is integral from 0 to infinity. You get 2 lambda, the sum goes inside, sum in k, and then you get the indicator function of 0 to ujk at lambda times nu jk d lambda. Okay, so this is monotone convergence. Okay, now this sum, lambda is fixed, then here you're doing the right thing. You sum some numbers, but these numbers are only giving a non-zero contribution if this indicator function evaluates to 1, and the indicator function can only evaluate to 1 if this size condition is verified. Okay? This can only evaluate to 1 if ujk is larger than lambda. Well, this is the only way that this thing can come 1. So now what am I doing? Now comes the crucial step in the argument. So I'm leaving the lambda integral as it is, and here I'm summing over a bunch of cubes, and all these cubes I'm ever going to see in my sum have the property that ujk in absolute value is larger than lambda. Now this sum I'm going to reorder, and I'm going to reorder it according to the maximal dyadic cube that these guys with a property are contained in. And so if I do the reordering, then I need to sum in M. Then I'm summing over the maximal dyadic cubes. And all cubes that are contained in here are contained in one of the maximal guys. So as a second sum, I should introduce Q contained in Q lambda M. Then I've been very generous. In fact, I'm going to throw every subcube of this maximal thing into the sum, no matter if they have the property or not, but everything I had before is going to be covered by that case. Okay, and that's the beautiful step here. And so once I've done that, this characteristic function is of no particular value for the argument anymore, because I have somehow taken care of it by looking at that. And then the new jk, I'm going to remember what that actually was. Well, new jk was over here. But I shouldn't use j and k anymore, because there's no j and k. There's just m and q. In terms of m and q, this is just the measure of the respective Carlson box, Whitney box. So for fixed cube, this is q times length of q over 2 length of q. Right? In the abbreviation, these were just the Whitney boxes associated to the QJK. Now the QJK is called Q, so I should write this. Oh la la! I love this proof. Now, I feel it's like the 100th time I'm using the same drawing. I'm just going to redefine what the base cube is. Okay? Now let me say that the base cube for the next thing would be Qm of lambda, and then this would be length of cube over 2, and the other thing would be length of q. Okay, just look at the same drawing again. Then I am summing the measure of these Whitney boxes over all dyadic cubes that are contained in Q lambda m. So Q lambda m is the big yellow one in my thing. So if I sum over all these cubes, these Whitney boxes, they are pairwise disjoint, and they are going to cover precisely the Carlson box over Qm lambda. So I can collapse the entire sum in Q, and I'm going to make these Whitney boxes all become Carlson boxes. One Carlson box for every m. So it's going to be the sum in m, and it's going to be the Carlson measure at Qm lambda length of Q m lambda over 2. Need to make it an interval. Okay. Length of Qm lambda. That's brilliant. You agree on this step? If not, let me know. Can you explain it again if there's a doubt? You have a question? Feel free to ask. At this point, you should see that I have managed to win against my principal enemy, namely overlap. Because I had all these boxes with the overlap, but I just filled all these boxes, these Whitney boxes, together so that they would form all these Carlson boxes. Okay, and now using the Carlson condition when I'm back to a Carlson box is of course much better, because I don't throw away anything, and the remaining boxes here, they're pairwise disjoint for every lambda, because that's written here. So at this point I'm using the Carlson condition. That gives me the Carlson norm of the measure times the integral 0 to infinity 2 lambda times the sum in m, the measure of Qm lambda d lambda. Now, these Qm lambda cubes, they're pairwise disjoint. So instead of writing a Lebesgue measure of sum of the Lebesgue measure of all these guys, I could write Lebesgue measure of the union of all these cubes. But all these cubes are contained in that set. So the union over all these cubes is also contained in the superlevel set of the dyadic maximal function. So I'm going to skip the step where I write it as a measure of the union. I directly go to the superset containing it. So I write 2 lambda times the Lebesgue measure of the superlevel set of the dyadic maximal function. And now? I'm ahead of schedule. I can wait until you answer the question. What should I do now with this? Might it be that this is something delicious? It's a layer cake. Yeah, of course. This is a layer cake formula. It's p lambda p minus 1 when p is equal to 2. It's a layer cake formula that gives the L2 norm of this function describing the superlevel sets. So this is equal to New and Carlson measure norm times A of u in L2 squared. But now A of u, we don't have it here, but you remember it was pointwisely controlled up to this constant c by maximal operator Hardy Littlewood type. So this is nu c times, what was it? It was the glorious omega n to the n over 2 squared times m of u. But the Hardy Littlewood operator is of strong type, is bounded on L2. Okay, so up to throwing another constant Cn into the game, we can eliminate the maximal function. And then we started over there, we proved precisely Carlson's lemma, and so this is the end of the proof. Do you have any further questions? Right, the proof is, I think it's a beautiful proof. And if you keep in mind that you have to win against the overlap, then actually the only thing that you really have to keep in mind is that you're going to order the cubes according to maximality with respect to averages exceeding a certain threshold, and that when averages exceed a threshold from above, then you are always in a superlevel set of some maximal function. And this is how maximal functions save the day in this argument. Alright, so if you don't have further questions, then we stop here. Thanks again for watching, if you watched the video. Thanks guys for coming here. Next week we might have another special guest giving lecture 10, and I'm not going to tell you yet what lecture 10 is going to be about. So see you next week before Christmas.